Ready? Have any of you ever felt bloated before? Have any of you ever let out a big old fart and you felt better? Arshawn, you should see Nicole's face. You have farted before. A lot of times in class, she'll go. She'll put her mask on even tighter. All right. Well, when you feel that bloated feeling, you might have a lot of gas buildup, and when you just let one rip, that gas is released and that pressure subsides. Well, pressure is defined as a force per unit area. Now, when it says per unit area, it could be like square inches, square feet, square meters, square yards, something. Per unit area. Any of the units of measurement that we use to measure area. Now, when we're talking about gas pressure, it's going to typically be gas particles that are exerting the pressure. Now, gas particles exert pressure when they push or when they collide with the walls of their container. So we're talking about your intestines, your lower intestines, your large intestines, called your colon. So if you just feel really, really bloated, you just got to let it out. That gas is pushing up against the walls of your colon, which is really building up a whole lot of pressure. We see this when we're inflating tires, bounce houses, balloons, you name it. The more gas you introduce to a container, the greater the amount of gas particles are in the container. The more gas particles that are in the container, the more gas pressure that there is in the container. Now, when I'm inflating my tire for my car, one little gas particle doesn't have a whole lot of pressure. But if you have like 10 to the 22nd gas particles, that's going to be a lot of pressure that can be generated. So an individual gas particle does not generate a whole lot of pressure. But when you just keep on pumping up and pumping up and pumping up and pumping up and pumping up, like just a liter of gas can have 10 to the 22nd gas particles. To give you guys an idea of just how big that number is, let's hash it out here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Hundreds, thousands, millions, billions, trillions, quadrillions, pentillions. This is 1 sextillion gas particles just in a liter. A liter, that's it. So when you're filling up your tires or a balloon or a bounce house, that's going to be an unfathomable amount of gas particles that are filling that up. And we talked how yesterday when you're pumping it up and pumping it up, imagine you're inflating a bounce house. The reason why it's inflating and actually taking the shape of a bounce house or other structures you're accustomed to is because the gas particles are pushing against the walls of the container. And they have nowhere to go. So they're exerting a force. That is known as gas pressure. So now let's move on to air pressure. We hear this in the meteorological sciences with the atmosphere. Earth is surrounded by an atmosphere. We all know that. And there's different layers of the atmosphere. There is a pressure that is generated by all the gases moving around in our atmosphere. Pressure generated by gases moving in all directions in the atmosphere is called atmospheric pressure or air pressure. Air pressure varies at different points on Earth. Now, have any of you ever been to an area of this planet where it is very high in the mountains, like Denver, or I've been to Quito, which is in Ecuador, the capital of Ecuador. Where have you been, Carson?
The Pikes Peak, Colorado, is like 13,000 feet.
Was it hard to breathe up there?
Yeah, I had to bring those air cans when I ran.
Why do you think it was harder to breathe up there? The air is thin. What makes the air thin? There's less air particles and there's less gravity. There's less air pressure. That's right. When I went to Quito, I was exhausted by just going up 3 flights of stairs. And when we got to the hotel, we had to go up the stairs to the 3rd floor. I was gassed because it was already more than a mile up in the mountain. And then we're hiking up this, just going up the stairs. And I'm from Florida, sea level, going this high altitude city. There's a reason why, and here's a little evolution lesson for you. There's a reason why all the natives in Quito, they were very short and very like barrel chested. Barrel chest means they just have a broader frame. Here's why they're short. It takes less effort. It takes less blood pressure to push blood throughout their bodies because they have very small bodies. Number 2, they have broader chests so that they can actually have greater lung capacity. So they can breathe that thin air and not get winded like me. So that was just tough. Well, here's why at Pikes Peak, or you go to Denver, Colorado, or you go to Quito in Ecuador, here's why the air is so thin up there. Gravity is greater on the surface. At sea level. And there are more gas particles there. Than there are at higher altitudes where the gravity is weaker. So pretty much air pressure is greater at sea level and weaker up in the higher altitudes, like in mountains and the higher levels of the atmosphere. Yes, Arshawn. It's colder just because there's less kinetic energy. There's less things moving. Now, if any of you ever want to hike, like if you want to go to the top of Mount Everest or Kilimanjaro, you need to bring an oxygen tank. The air is going to be so thin that you will not have enough oxygen circulating through your blood to keep you conscious. You will black out. Not because you're exhausted, not because you're scared, no, you're going to faint, just because there is literally very little oxygen out there. You're basically being choked. You need enough oxygen circulating to your brain to maintain consciousness. Once there's not enough oxygen in your brain, you're going to pass out. Well, in Denver, Colorado, where the Broncos play and the Colorado Rockies baseball team plays, it just so happens that every year in baseball, one of the top 5 baseball stadiums in home runs is Coors Field in Denver, Colorado, because the air is actually thinner up there. What that means is, try to imagine this. There are less gas particles. When I throw this ball at Kevin, ready? As that ball was traveling through the air, it was colliding with billions and billions and billions and billions of gas particles, which caused it to slow down. We're back. Now, if we were sitting in Denver, Colorado, and I gave the same effort in that toss, it would probably have gone further because the air is thinner. There's less gas particles that are colliding with this ball. And so when you hit a home run in Denver, Colorado versus St. Pete, where the Rays play, there is literally less gases that the ball is colliding into, less things to slow it down, which means it's going to travel further. Whenever I play fantasy football, guess whose team I always look at to see if they have a good kicker? The Denver Broncos. Because when they kick field goals, the air is thinner, so the ball travels further. One year I won fantasy, I had the Denver Broncos kicker because he was kicking 50-plus field goals all the time because the air is thinner up there. When the Bucs played in Denver this year, they had this big sign on the visitors' locker room that said, "Air sickness is real." They're trying to intimidate their opponent. You had a team coming from Florida, coming up into the mountains, and the air is thin. You got tons and tons of oxygen tanks on the sidelines, and they were interviewing the players. The Bucs beat the Broncos this year. Like, what do you think? Have you ever been to Denver before? No, man, I've never been to Denver before. What do you think the air quality? It's thin. I was exhausted from warm-ups, just stretching. And so it is real. It's a real thing. The air is thinner because there's less gravity. And when they say thinner, there is less gas up there, which means that things tend to travel a lot further. Again, if I threw this ball at Kevin with this same effort, we're here at sea level. If I did that same little toss, it would probably go over his head because there's less things crashing into that ball. All right. Now, let's talk about measuring air pressure. There's instruments that actually do this. What meteorologists use is called a barometer. This is an instrument used to measure atmospheric pressure using a mercury column. Do you remember what the symbol for mercury is? Hg. So changes in air pressure are going to cause, changes in air temperature and humidity cause the air pressure to vary. During the hurricane season, when we're watching a storm coming out of the Gulf of Mexico or the Caribbean or the Atlantic Ocean, if the meteorologist says that the atmospheric pressure inside the hurricane is dropping, that's bad. Bad weather is low pressure. And so if a storm is experiencing a decrease in pressure, that means its barometric pressure is falling. That means the storm is getting stronger, because the stronger storms get, the lower their pressure goes. Good weather is high pressure. Bad weather is low pressure. And so if you were to watch a hurricane update and they said on Tuesday, you don't need to write this down. On Tuesday, the hurricane had 1,100 millibars. And then on Thursday, it was down to 900 millibars. That means the hurricane is getting stronger. That's not a good sign. We want that air pressure to increase. because when it increases, it's getting to be more favorable weather, which is nice. When you look on a weather map, if you ever watch the weather, guys, a big blue L means low pressure. The big red H means high pressure. High pressure is nice weather. Low pressure is nasty weather. In fact, I bet some of you have experienced this before. When you walk into Target or Publix and the sliding door opens and it feels like the air conditioner is blowing in your face. And then you walk into the store and it's like it never happened. What's going on? That is the difference in atmospheric pressure. So imagine this. You walk into Target, okay? There's Target. And let's say that the atmospheric pressure inside Target is about 1,500 millibars. Let's say that it's a kind of nasty weather outside and the air pressure outside is 1,000 millibars. I want you to think of basic diffusion here. Which way would gas want to go? From 1,000 to 1,500 or from 1,500 to 1,000? It always goes from high to low. That needs to be burned into your brains. Diffusion, passive diffusion is always going from high to low. So when these doors open on the automatic entrance, it's going to feel like the air conditioner from the store is blowing in your face because gases are going to be leaving. It wants to equal out. The air pressure outside is less than the air pressure inside. And so that's going to result in diffusion of gas particles until you reach an equilibrium. But let's be honest, a store is not going to get to equilibrium with the outside world. So you're just going to feel like the air is blowing in your face till you step in, and then you're in an entirely different air pressure. How about this? Let's say that you're in an airplane. You're at Tampa International. And I'm going to use a different unit of measurement here for you. You're going to get on an airplane, and here at sea level, we call this 1 atmosphere. An atmosphere is a unit of measurement for measuring the air pressure. And so when the door seals on the airplane, it is a sealed door. It is 1 atmosphere inside the airplane. So the airplane takes off, and now they're at about a cruising altitude of 36,000 feet. So the airplane's way up in the sky. And let's say that the air pressure is 0.6 atmospheres. Inside, it's 1 atmosphere. If somebody punches a hole through the wall of the airplane, which way are gases going to flow? From the atmosphere into the plane or from the plane into the atmosphere? Carson? It's going to go from the airplane to the atmosphere. Gases are going to want to diffuse out, which is why when you see those movies or shows where a plane window is open, everything gets sucked out, or like the movie Alien, where they kill the alien by opening the hatch and the alien gets sucked out into space, because the air pressure in the vehicle is greater than the air pressure outside the vehicle, and diffusion wants to go from high to low. That's just how air flows, from high to low. But this is why they seal that door. So in the event that the door opens, everything's just going to get sucked out until you reach an equilibrium. If you're able to hold on for dear life while everything's getting sucked out, eventually the inside of the airplane will equal the air pressure outside the airplane. And if that does happen, then the airplane itself inside would be at 0.6. Eventually it will equalize. Yeah. Up in the atmosphere? Because you have to have air pressure at a certain level for you to breathe. Why do you think they drop the oxygen masks when the airplane has a rip, like a hole in it? Because the air is very thin. There's not going to be enough air to keep you conscious. And so the oxygen mask is going to give you a healthy supply of oxygen and a proper pressure to keep you awake. Yeah, Sarshan. Well, it can be, but that's just going to be an opening. Air is circulating, and it circulates out. All right. So as I said, high pressure is nice weather, and low pressure is bad weather. So when you're watching the weather report, they mention high pressure, it's good. Low pressure, not so good. Yes? No, that's called isotonic, and that's going to be no difference. Okay, so I mentioned atmospheres. Let's talk about units that measure pressure. I'd like to show you guys just a few little fun movie clips of things getting sucked out of a room or an airplane. The first one, now keep this in mind, everybody. This is called a Pascal. Its abbreviation is PA. This is the SI unit of pressure. When you hear SI, what system is that? That's the metric system. In the metric system, we use pascals. This is named after the French scientist, what's his name? Blaise Pascal. We really don't use pascals, we use kilopascals, which is lowercase k, capital P, lowercase a, kilopascals. How many pascals are there in a kilopascal? There are 1,000 pascals in 1 kilopascal. This is what the international community uses to measure air pressure. Another unit of measurement that we use is called millimeters of mercury. Now, I'm going to help you avoid making a very common mistake that many chemistry students make every year. And unfortunately, despite my warning, some of you will commit this mistake. Ready? Here it is. I'll ask you, what is the SI, aka metric system unit for air pressure? And some students will say, oh, millimeters of mercury. I said, why do you say that? Because it says millimeters. I would say, milli what? Meter. Okay, what does a meter measure? Distance and length. You are measuring the distance that the mercury rises and falls on a barometer. That's the distance. Just because it says milli doesn't mean that that's the one that we're using. Pascal is the one that's used in the metric system. On a millimeter of mercury, you have a barometer, and the pressure rises or drops it's indicated by the mercury going up or down. And then the third one, everyone, is called, actually the third one is called atmospheres. I just mentioned that. This is abbreviated ATM. And one that we're seldom going to use in this class is called TOR. Its abbreviation is also TORR. It's basically the same as millimeters of mercury. Like the conversion is a 1-to-1 ratio. Okay, so we're here in Florida, Tampa, Florida. Let's try to figure out what our air pressure is here. And this is going to be your conversions. You guys are going to do a little bit of math, but these are going to be the units of pressure at sea level. Sea level is where the water meets the earth, meets the land. So for atmospheres, the number is 1. We're at 1 atmosphere here in Tampa, Florida. For kilopascals, we're at 101.3. Here in Tampa, Florida, we're at 101.3 kPa. For millimeters of mercury, we are at 760 millimeters of mercury at sea level. And for TOR, as I told you, it's the same thing as millimeters of mercury, 760. These are the units of measurement. They're all equal to each other here at sea level, and it only decreases as you go up. I think in Denver, Colorado, they're at 0.8 atmospheres, which means I think they're at like 90 kPa. We can do the conversion. I don't have my Siri with me. I can use one of yours though. Let's see, whose phone is on? Here we go. Hey Siri. Oh, she can hear me back there. Okay, cool. Let's try it again. Hey Siri. What is the air pressure in Denver, Colorado? What did she say? I don't want 30.7 inches. I want millimeters. Well, let's write that down. Hey Siri. How many millimeters is 30.7 inches? She said 30.07? Okay. Hey Siri. How many millimeters is 30.07 inches? All right, we'll stick with that. 763. Okay, I want you guys to get your calculators. I don't think this is right. It should be less. I want you to convert 763 millimeters of mercury to atmosphere. So this is just a good little practice problem. The number should be less. I think she's mistaken somehow. What is the conversion of millimeters of mercury to atmospheres? Well, it's 1 to 760. So you'll put 760 millimeters on the bottom. You will put 1 atmosphere on top. There's your conversion. And then just do the math. So I need one of you to tell me, what is 763 divided by 760? 1.003139. All right. So it's pretty close, but these are conversions that you are going to be doing. They're very simple. I'm going to make up a couple just for the heck of it. Let me ask her this. Hey Siri, how many atmospheres is Denver, Colorado? Let me look here. Hold on a sec. We're gonna look something. Let's look at Mount Everest. All right, let's see. Air pressure at peak of Mount Everest. Ooh, okay. 253 millimeters of mercury. I want you to convert that to atmospheres, and I want you to convert that to kilopascals. So you have to do 2 problems. This is just to see if you can figure out how to do the conversion, guys. This is just a little practice setup. I'm going to ask Kendall and Derek to help us solve this in a moment. 10th place. Or actually, rounded to 3 sig figs. Whatever it takes to get 3 sig figs. Kilopascals and atmospheres. I'm going to try to find this. At what air pressure is breathing impossible? Okay, 30,000 feet. Air pressure at 30,000 feet. Ooh. Okay, got it. All right. So, Kendall, what did you do? Which one do you want to do? Do you want to do kilopascals or atmospheres? Okay, so what conversion did you do?
I did 1 atmosphere over 1.
No. I gave you 253 millimeters of mercury, so you need to convert millimeters of mercury to atmospheres. Let's do atmospheres. So what is the conversion between atmospheres to millimeters of mercury? All these numbers are the same. So 1 atmosphere is equal to how many millimeters of mercury? That's the conversion. So where do you want to put the 760 millimeters of mercury on this conversion table? On the bottom. Let's work out the kinks here today, guys. What would you put on top? One what? One atmosphere. Millimeters of mercury cancel out. So Kendall, what is 253 divided by 760? I have 0.333 atmosphere. Okay. Derek, let's convert millimeters of mercury to kilopascals. What is the conversion for that?
I did 101.3 to 760
Good. Okay, where did you put the 760?
on the bottom.
Good. And what goes on top?
101.3.
101.3. Very good. Okay, millimeters of mercury cancel out. So what math do you have to do here, Derek?
Multiplication.
So tell me. Say it.
Do 253
Yeah,
101.3 divided by 760.
that's it. Okay, this is going to equal 33.7 kilopascals. Now, I just looked up online. At what atmosphere or what elevation does it pretty much become impossible to breathe? I have 30.0. No, I have 30.1 kPa. At that pressure, you really can't breathe. So, can you breathe on top of Mount Everest? Barely. Like, you will still probably pass out. You're going to need an oxygen tank. You'll barely be able to breathe. What?
Breathe more higher. Okay.
Yes.
So if someone from like, from just some place that lives in a lot farther above sea level, they fare a lot better than us if they went to climb on Everest, just based on like getting used to it.
Yeah, I guess so. Okay, so that is just units of pressure. Now to finish off today's class. Actually, let's try one more. I'm trying to think of a place. Let's see. All right, let's do Quito. Elevation, or let's say air pressure in Quito, Ecuador. This is where I went. Okay. 1028 millibars to kPa. All right, guys, got it. Here we go. This makes no sense. All right, I got it. It's 87 kPa. I want you to convert that to millimeters of mercury. I want you to convert that to atmosphere. Do that now. And then we'll do the last little bit. Okay, for millimeters of mercury, you hopefully got 652. which if you want to get the proper sig figs would be 650. And for atmospheres, I have 0.86 atmospheres. So that's just basic conversion, one-step conversions. You guys get those two problems? Any trouble? Okay. Last little section notes for today is one little last problem. It's an addition problem. It's like one of the easier ones in this year. Dalton's law of partial pressures. Dalton discovered that each gas in a mixture exerts pressure independently of the other gases. So they all basically exert their own force without the others. Dalton's law of partial pressures states the total pressure, which we're going to call P total, is equal to the sum of the pressures of all the gases in the mixture. So it reads a little bit more difficult than what it actually is, guys, but your pressure for your total is simply going to be your first gas pressure plus your second gas pressure plus your third gas pressure plus your fourth, and so on, so on, so on, so on, so on. That's all you do. You just add up the pressures. The one thing that you need to be sure that you're doing is that all the pressures from the same unit of measurement. You can't add one pressure that's measured in atmosphere and then another one in kilopascals. You have to make sure that they're all the same unit of measurement, whether it's kPa or millimeters of mercury or ATMs. So I have one practice problem for you. I think this is going to be very simple for you. I'll let you all finish up writing those notes, and we'll do an example problem, and that should be it for today. We're right on schedule. You ready? All right, we have 4 minutes left. Here's an example problem for Dalton's partial pressures. A mixture of oxygen, carbon dioxide, and nitrogen has a total pressure of 0.97 atmospheres. So what this is going to look like, guys, is let's call oxygen A, let's call carbon dioxide B, and let's call nitrogen C. All this is going to be is A atmosphere plus B atmosphere plus C atmosphere is going to equal 0.97 atmospheres. That's all this is. Now, I'm not done yet. In this problem, oxygen is its partial pressure is 0.70 atmosphere. Nitrogen's partial pressure is 0.12 atmosphere. I want to know what the pressure of carbon dioxide is. So our known values. Your P total is 0.97 atmosphere. Your pressure for oxygen is 0.70. And your pressure for nitrogen is 0.12. Your unknown is the pressure for carbon dioxide. Jade, how do I find our missing one? So basically we have A plus B plus C equals 0.97. We have A and B, we're missing C. What do I do?
Add the nodes together and subtract it from the
Add all three knowns or the partial pressures? Okay, so 0.7 plus 0.12 equals 0.82 atmosphere. What do I do now?
subtract it from the total.
Subtract that from the total. 0.97 atmosphere minus 0.82 atmosphere is going to equal 0.1, nope, what am I doing? 0.15 atmosphere. That is going to be CO2. That's it, addition and subtraction. You add up the parts to get the whole. It'd be no different than if I said Jade plus Max plus Colby together weigh 500 pounds. If Max equals 100 pounds and Colby weighs 100 pounds, how much does Jade weigh? 300 pounds. It's just like that. All right. We are done tomorrow.